So what actually is the big O notation? A lot of you might have also heard it being called the time complexity. So in simple terms, big O notation is nothing but a simple measure of how efficient or fast the algorithm is. But measuring the speed of an algorithm is not as straightforward as you might think. Let's look at a simple example.
Sam and Max are looking for their friend Bob, who is hidden in one of the 9 neighboring houses. Sam searches the houses from left to right, while Max searches the houses from right to left. Now Bob is hidden in the fifth house. So Sam starts her search, and since she takes around 2 minutes to search a house, she finds Bob in 10 minutes. Now it's Max's turn. Again, Bob is in the fifth house. Now Max starts his search from right, and since he's a bit faster than Sam and more athletic, he only needs 1 minute to search a house. So he finds Bob in only 5 minutes. Now, if we just go by the time, it would seem that Max's algorithm is better, right? He only took 5 minutes instead of 10. But even just with intuition, we can tell that searching from left or right doesn't really matter. And Max took less time not because of his better way of searching, but just because he was faster. It's the same with algorithms. You might have two algorithms which are essentially the same, or maybe even one of them 10 times slower. But if the slower one was run on a computer that is 100 times faster, one might falsely claim that this algorithm is better. To understand that, let's look at one more scenario. It's a very common example when teaching about algorithms. So let's say Sam and Max and Bob are playing a game again, where Bob thinks of a number between 1 and 100, and Sam and Max have to guess the number. After every guess, Bob tells them if their guess was higher or lower than the target. This time, Max goes first and starts guessing all the numbers from 1. Bob thought of 35, so after 35 guesses, Max finally managed to get the correct number. Next up is Sam. Now, Sam thinks of a clever trick. Since after every guess, Bob has to tell her if the guess was higher or lower than the target, this info can actually be used to make the guess better. So, Sam starts by guessing 50, the middle number. And when Bob tells her the guess is high, she knows that the target number is less than 50 and she can eliminate all the options from 50 to 100. Next, she guesses 25, the middle of the remaining possible numbers. This time, Bob says this is lower, and with the same logic, she can now eliminate the numbers from 1 till 25. Continuing like this, she reaches the correct answer in around 6 guesses. So now, even if I don't tell you how much time each of them took, you can tell that Sam's approach is much better. But what did you compare if not time? Is the number of steps. Even if we do not know exactly what time each of the persons took, just by looking at the algorithms, we can say that Sam's algorithm will take much fewer guesses, even for very, very large numbers, as it eliminates almost half of the options for every guess. So now we are on the right track. As you can see, even if we have two different computers, an algorithm that takes less number of steps overall to complete will generally be faster, eliminating the bias that comes from different types of hardware. But still, does that mean that Sam's algorithm is always going to be faster than Max? The curious students among you might have already noticed that if Bob has chosen the number 1, Max would have guessed that number in just one guess, while Sam would still have taken around 7 to 8 guesses. But that does not mean that Max's algorithm is better, right? We already know how much more efficient Sam's algorithm is. So what's happening? It's just that in particular cases, different algorithms might take different number of steps to complete. To be able to finally compare them properly, we'll have to compare them in a single type of a case. That's why we always consider the worst case scenario. That is the maximum number of steps this algorithm can take. Coming to our example, the worst case scenario for Max's algorithm is when Bob chooses a number that is the last. If he was choosing a number between 1 and 100 and he chose 100, Max would have to make 100 guesses. If he chose a number that is 5,000 or 10,000, he will have to make that many guesses. So as you can see, there's a pattern emerging here. Max's algorithm is linearly proportional to the highest possible number. So in other words, we can say that if n is the biggest number Bob can think of, then in the worst case, Max's algorithm will take n guesses to complete. In terms of big O notation, we call this type of an algorithm O of n. For Sam's algorithm, as you have already seen, it cuts the possible number of options in half every guess. The worst case scenario for that would be, again, if Bob chose the first or the last number, and if you apply some mathematics, you can get the answer that that would require log base 2 of n number of guesses. So if n is the highest possible number, let's say 100 for this example, the maximum possible guesses that Sam would need using this algorithm would be log base 2 of 100, which is around 7. So this type of a algorithm in terms of big O notation is called O of log n. So now we are super close to understanding what big O notation really is. Now you might think it is the number of steps the algorithm takes. But as we saw in the previous example, that is a good measure of an algorithm's speed, but the number of steps still depend on the size of the data. So in big O notation, what we are actually measuring is not the number of steps, but how the number of steps the algorithm takes grows in relation to the size of the input data. For an algorithm that is O of n, if the size of the data set is n, it would take n steps. It grows linearly with the size of the data. For an algorithm that is O of log n, the number of steps grows much more slowly, even if n becomes very, very large. So coming back to Sam's algorithm, what Sam was actually doing is a very famous algorithm called binary search. Some of you might have noticed that there was a slight mistake. If someone actually sat down and counted how many steps it took, Sam actually needs log of n plus 1 steps in the worst case scenario. But then why did we write O of log n and not O of log n plus 1? Because again, that is the main point. We are not calculating the exact number of steps the algorithm would need. We are actually just measuring the growth of the number of steps in relation to the size of the data. And when we take into consideration very, very large data sets, that plus one does not even amount to anything. So that why we can just ignore that. So in essence, this is what big O notation is. Big O notation is just a way to measure the efficiency or the speed of an algorithm, but we do not measure that in terms of time or in terms of how many steps you take. Instead, we measure that in terms of the growth of the number of steps it would take with respect to the size of data. In the next video, we are going to explore some common types of big O notations like O of n squared, O of n factorial, etc. We'll see what the time complexity is for some famous algorithms, and we'll also look into how you can find the time complexity of your own algorithm. Thanks for watching. See you in the next one.